So let's just go through this, this last step. So we want to show that this program is a special case of an SOCP. This is a quadratic program. I've just rewritten the standard quadratic program in this form, where usually we have in the criterion like 1/2 x transpose qx. Now I've introduced a second variable, call it t. It's just real valued. And I've added t to the criterion in the place of that quadratic form. And I've added a constraint that that quadratic form should be less than or equal to t. So that is actually equivalent to a quadratic program, right? We can see that that's the solution. Well, we're going to be minimizing c transpose 1/2 x transpose qx. That t is just playing a role here for convenience, this reparameterization. So we want to show that this is a SOCP. So what constraints do we have here that aren't valid? So, or what form is not valid? So what part of this form is not valid? So this is fine, because remember an SOCP is of this form, has a linear criterion, and we allowed to have. Notice that we're allowed to have equality constraints. We're also allowed to have linear inequality constraints, because, for example, I could take this matrix di, and this if I wanted to, I could take this little di to be 0, and then this is just introducing an inequality constraint on my variables. So inequality constraints that are linear equality constraints, and a linear those are all fine in SOCPs. Any other inequality constraints we have to be of this form, the second order cone form. So here, the only thing that's kind of violating SOCP form is this bit, right? Because it's not a linear inequality constraint, and it's not the norm of some linear transformation of our variable being less than or equal to a linear function. So this is the key step that I wrote down here. It turns out we can actually rewrite that constraint in the following way. So basically, we're just going to, so remember x and t are our variables. Let's think about a matrix q to the half, which has the property that q to the half is symmetric, and q to the half times q to the half is equal to q. That's called the symmetric square root of our matrix. If q is positive semi-definite, then we can always find such a matrix. And I'm going to rewrite then this constraint that x transpose x is times a half is less than or equal to t in the following form. So let me just write it on the paper. We have a little more room to play with it. So it's just q to the half times x divided by square root of 2. That's the first block of my variable. And actually the last block of my variable is just 1 plus t over 2. So I claim that actually the 2 norm of this thing being less than or equal to 1 minus t over 2 is equivalent to this constraint, 1/2 x transpose qx is less than or equal to t. Okay, so we're just going to check that. And notice that this is a valid constraint in an SOCP, right? Because this is, my variable is x and t, and this is a linear transformation of my variable, this thing right here. And I have a linear transformation of my variable. I take the L2 norm, I compare that to a linear function of my variables. That's valid for an SOCP. So let's just square both sides, right? Square both sides in order to show that this is equivalent to that quadratic constraint. So on this side, I get 1/4 plus t squared over 4 minus t over 2. Right, if I square that, because I have minus 2t, but it's divided by 4, so I get minus t over 2. And on this side, if I square this, I can think about just taking this vector and doing this vector transpose itself. So then I get x transpose q to the half times q to the half times x. Here I've used the fact that q to the half is symmetric, right? This would usually be x transpose times q to the half transpose q to the half times x divided by 2. That's this bit transpose itself, and then from this I just get 1/4. It's just this squared, right? 1/4 plus t squared over 4 plus t over 2. Let's see. I wanted to have maybe I actually wanted to have the minus sign on the left-hand side. So we're going to see what ends up coming out. And we may have to replace t with minus t to get the answer. But in any case, all this stuff cancels, right? I have no dependence on t squared. And this is just 1/2 x transpose qx. And I guess it does look like I had the sign of t wrong. But we can see that I just move this over to this side, and I get minus t. So we've expressed the constraint that 1/2 x transpose qx is less than or equal to minus t in terms of an SOCP constraint. So what you should actually do is just replace t with minus t to get the constraint 1/2 x transpose qx is less than or equal to t. So I guess I'll correct that again in the slides, but this should have been 1 minus t over 2, and that's 1 plus t over 2. Okay, so that was just the demonstration that a QP is actually an SOCP. And let's see if I don't have the picture, so let me go back to the picture then for you. So this is our picture of the hierarchy, just so that you are reminded. And what we actually showed is that to go from QPs to STPs, we introduced another class of problems, which is called second-order cone problems, that lie in here. And we just showed that QPs were a special case of second-order cone problems. And the rest of the hierarchy we'd established last time. Okay, so that's the hierarchy of convex problems. Any questions about that before I move on to gradient descent? Yeah.
So from a practical perspective, you were saying that QPs are still fairly easy or more well formulated to solve through solvers, but not STPs. Where do SOCPs fall in that? Like, are they typically
Yeah,
easy to?
it's a good question. SOCPs are usually pretty hard. So I mean, this is all kind of a non-rigorous, these are all non-rigorous statements. But I think generally speaking, STPs are really hard, and conic problems are really hard. And unless you have very special cases of STPs, then you shouldn't expect to solve an STP in 10,000 variables. That would, like a general STP in 10,000 variables, may be like really prohibitive. But QPs, like arbitrary form QPs, like the biggest limiting factor in QPs for solving them is, well, depending on how you solve them, is maybe matrix linear system solving, so matrix inversion. And we can still do that when those matrices are very large, especially if we do like a system solves and stuff. But when we talk about algorithms, I guess you'll get a better sense for certainly some of this stuff. But like interior point methods, which are the way that we typically solve STPs, they can be very expensive for large arbitrary STPs. And SOCPs, I think, too, are generally I think of them as quite expensive. So there are some STPs that are like really not very expensive. An example of that, for example, is the graphical lasso. That's an STP that's pretty cheap. We probably will talk about that at some point in the class. So there are definitely cases of STPs that we can solve efficiently. Other questions? Okay, so that was our kind of fundamentals unit. Talked about convex sets, convex functions, convex optimization problems, and canonical problem forms. So that hierarchy we just saw. And now we're going to move into our first algorithms unit, where we discuss algorithms for optimizing a lot of these problems. And this whole unit is going to be focused on first-order methods. We'll get a precise definition of that. I think maybe, if not in this lecture, then very soon. But basically, think about methods that use the gradient, not the Hessian. That's what a first-order method is, let's say, very roughly speaking. And of course, the simplest and maybe most natural first-order method is gradient descent, which will be the one we talk about today. So, okay, just to remind you what we did last time, LPs are of this form. QPs are like an LP but with a quadratic criterion instead of a linear criterion. SDP is like an LP but with matrices. That's the way we tried to think about them. And a conic program is the most general. And we talked about all these last time. So to solve kind of general form LPs or general form STPs or even QPs, we are not going to be able to do that until we talk about interior point methods. We can solve special cases of these with first-order methods, but not all of them. And hopefully that'll become clear in a bit. So we're going to talk about unconstrained smooth convex optimization today. And next time, we will talk about what happens when our functions aren't smooth. And then we'll talk about what happens when we have constraints, and then the combination of non-smooth with constraints. But today, we're just going to focus on constraints and smooth optimization. And that means that this function we're assuming is, let's say, differentiable. And just for simplicity, we're going to take its domain to be all of Rn. Nothing's really going to change if that wasn't true, but just for simplicity, I like to make that assumption. And just to remind you, we denote the optimal criterion value by f star and a solution by x star. There may be more than one solution, right? It's not, I haven't declared that this function is strictly convex, it's just convex. So gradient descent is hopefully a method that is at least familiar looking if you haven't seen it before, but I don't think it really matters if you haven't seen it. We'll talk about it in detail today. I think it's just a pretty natural method that you would have seen in potentially in other courses. So the idea is to choose some initial point. It doesn't really matter what initial point, at least for the purposes of guaranteeing convergence. We just choose some initial point, and we repeat the following steps. We look at the point that we're currently at. I'm going to note that by x, superscript k minus 1. We evaluate the gradient of our loss function at that point, and we move in the direction of the negative gradient. Okay, so we multiply that by some step size tk, and we update our variables by moving them in the direction of the negative gradient. And we call that xk, and then we repeat. Okay, so think about it as repeatedly going downhill. The negative gradient is going to be pointing in a direction that decreases the criterion. If we made an infinitesimal step in that direction, the criterion should decrease. And so modulo choosing the step size is appropriate. Just if we kept following the negative gradient, we should get to the minimum. That's the intuition behind gradient descent. Okay, and we're going to stop at some point, although I'll be vague about that until a little bit later. So here's a picture of gradient descent. You probably have seen this picture like 2 or 3 times so far. But what I was showing you was actually the gradient descent paths for a quadratic function in 2 dimensions. So this is just a quadratic surface. I have a 2-dimensional optimization problem, and I'm showing you what gradient descent, the path would look like if I were to start at various points in the space. So I picked 5 points, and I colored the paths differently so you could identify them. And this is just taking very, very small steps. I've just drawn the progress after very, very small steps when tk is very, very small, so that it looks like a continuous path, just so you can kind of visualize it. Okay, so what we see is what we maybe would expect, which is for a convex function, it doesn't really matter where we start. We're going to get to the global minimum, or a global minimum, if there was more than one, eventually, with gradient descent. Okay. This is an example of gradient descent for a non-convex function in 2 dimensions. Again, we've seen this picture just to motivate convexity and non-convex functions. But now I can tell you precisely what it is. It's, again, just gradient descent on a non-convex, 2-dimensional non-convex function. And you can see that what happens is, depending on where I start, I end up at very different local minima. Right? So here I've started in this purple starting point. I end up actually at this local minimum. Here it's not clear where I'd end up. Actually, the path would have continued off of the display, so I just kind of stopped looking at it. Okay, so this function has many different saddle points and local minima. It's non-convex, and it's really unpredictable what gradient descent is going to do. It depends on the starting point. So we're going to focus on convex functions, as is kind of our motto, of course, throughout the semester, just for this reason. There we go. Okay, so what's the interpretation of gradient descent? Let's talk about that first. Turns out we can interpret it via kind of a quadratic approximation to our criterion function at each step. So suppose as a function of y, suppose I'm at a point x. Okay, I'm at a point x right here. And I had my criterion function looked like something. But I'm going to actually make a quadratic approximation to my function. So I'm going to think about at points y. I didn't do a great job of drawing that. But at points y, I'm going to think about this quadratic approximation, which is given by f of x plus the gradient of f of x transpose y minus x plus 1 over 2t times the norm of y minus x squared. So this is very much like a second-order Taylor approximation, right? If I had a second-order Taylor approximation, then actually I would have replaced this term. So second-order Taylor replaces with 1/2 y minus x transpose the Hessian times y minus x. Right, that would be the usual term in a second order Taylor approximation. Here I've actually, you can think of it as replaced the Hessian with just the identity matrix times 1/t. That's what I've done. So it's a very simple quadratic approximation to my function. It's not, doesn't have the curvature given to me by the Hessian. It's just a very, I have a very simple notion of how curved my function is. Just replace the Hessian, that's why I say here, by 1/t times identity. And what I can think about gradient descent as doing is actually choosing the next point to minimize this quadratic approximation. So I'm at x, and suppose I want to update, my optimization procedure is going to choose a next point, and let's call that next point x plus. So this would be like xk, and that's xk minus 1. It's just a different way of writing it. And x plus is actually, you can think about it as chosen to minimize this quadratic approximation over y. Okay, so over all y, I look at the point that minimizes it. And that point is actually this guy, x plus, which is just x minus t times the gradient of f of x. Okay, to check that, you can, this is a convex quadratic function. So to minimize it, we can just take its gradient and set it equal to 0. And remember, this is a function of y we're thinking about. X is fixed here. So just take the gradient with respect to y. What do you get? You just get the gradient of f of x. You get nothing from that first term. You get the gradient of f of x from that second term. And from here, I get 1/t times y minus x. So rearrange for y, and you'll see that y, which we're calling x plus right at the minimum, is exactly just x minus t times the gradient of f of x. It's exactly this point that minimizes that. So how do I think about that quadratic approximation? I could think about it like taking the Hessian and replacing it by something simpler. I could also think about it in this way, that I'm thinking about this quadratic approximation is composed of two parts. The first part is a linear approximation to my function. Right? That's exactly this. It's just what happens if I would have approximated my function by its tangent line at x. And the second is a proximity term. So of course, we can't minimize a linear function. That will send us off to infinity somewhere. But we can add a proximity term, which is saying we don't want to be ending up too far from where we are right now. Right? And that proximity term is going to kind of pull the next gradient step so that it's well defined and somewhat close to x. And exactly how close to x it is dictated by this weight. Right? So if t is very, very large, then I'm essentially placing very little weight on this proximity term, and my steps are going to be very large. You can see that from the results of the steps. If t is small, then I'm placing a lot of weight on being close to where I am, and the steps are going to be quite small. Okay, so that's another way of interpreting the gradient descent steps. What happens if I didn't replace the Hessian by the identity times 1/t, and I just used the Hessian itself, and I tried to minimize that quadratic approximation? Who can tell me what that would be called, or what that would be doing? Right, that's just Newton's method. So we'll learn that in the next algorithms unit. But if I just use the Hessian itself, which is also valid, that's called Newton's method. And it's more expensive, but it has faster conversions. Okay, so that's just a picture of what I just said. Think about, I'm at the blue point, that's x. I make a quadratic approximation to my function. That's this dotted line. My function is this solid line. And the next gradient descent step is in red. It's chosen just to minimize that quadratic approximation. Okay? Yeah?
I didn't get why minimizing the quadratic form necessarily reduces the overall value of the...
Oh, we didn't say that actually. So the question was, why is it the case that the criterion at x plus is lower than the criterion at x? Is that the question? Yeah, so I haven't proved that for you yet. I'll prove that when we talk. Today we're going to do convergence analysis of gradient descent. So you'll see that that's the case kind of formally as long as we choose t appropriately. But you can also think about it in the following way. I mean, it is the case that if t is small enough that it's going to reduce the criterion. That's the definition of the gradient, right? The gradient, if I go in the direction of the negative gradient infinitesimally, the function has to decrease by definition of the gradient. if you remember what that means in terms of like the directional derivative. So it's just a question of making t small enough. If t is really large, I could definitely overshoot, right? And I can make the function higher. It's a good question, yeah.
What's the motivation for us to introduce the Taylor expansion here?
Well, the Taylor expansion is motivation for gradient descent, but you meant why are we using the Taylor expansion? Well, I think it provides a way of understanding what this step is. I mean, you could say the step is reasonable from first principles, but another way of deriving the step is to start there, right? Like, let's suppose you decide you want to invent your optimization algorithm so that it minimizes something like a quadratic approximation to your function over and over again. Turns out that would be gradient descent if this is how you chose the quadratic approximation. Okay, so there's another way of ending up at these updates. And in fact, this motivation is going to be important for proximal gradient descent, which we'll talk about in 3 lectures or so. Because we'll derive a new algorithm basically from this motivation. It's a fair question. Other questions? Okay. So here's what we'll talk about for the rest of today. How to choose those step sizes, t. We'll do a convergence analysis. That'll be the first time we actually prove that an algorithm converges and has a particular convergence rate. It may be the only time we do it in this unit. I don't think I'll do it for the other methods. Although on your second homework, you will do it for us for proximal gradient descent, or I guess for yourselves. It's not like we are missing that proof, but you'll prove the rate for proximal gradient descent on your homework. And then I think when we talk about second order methods, we'll probably do a convergence rate analysis for Newton's method, just to give you an idea of the differences between second and first order methods. And then if I have time, I'll talk about gradient boosting, although that's not critical. That was just supposed to be a fun connection to machine learning. And I wanted to introduce stochastic gradient descent as well. So let's talk about how to choose these step sizes. OK, the first thing you might try, which is the simplest thing arguably, is just to fix the step size to be something, just some value and never change it across the iterations k. So if t is too big, if I fix all the tk's to be some common value t, and that's too big, then it can diverge. OK, so here's an example of what happens in 2 dimensions. Let's actually just do an example in 1 dimension first. OK, suppose I'm trying to minimize, say, this function, and I'm here, and I try to take a step in the direction of the negative gradient. So remember, OK, the gradient in 1 dimension is just the derivative. In which direction does the negative derivative point? It's this direction, right? So I'm going to move my current point, like let's call this xk, or xk minus 1. I'm going to move it in this direction. You can see just kind of intuitively that if I move too far, like let's suppose I take a step all the way out here, somewhere out here, then I'm going to be at a higher value of the criterion. Right? And if I now evaluate the negative gradient and it points in this direction, if I move too far again, I'm actually going to be ascending up the function. I won't be doing descent. So if the step size is too large, then gradient descent can diverge. And that's what's happening in this picture. It's just a little more, it's 1 higher dimension than this picture. So in this picture, I have a 2-dimensional function, and I'm drawing to you the contours of that function in 2D. So each of these is a set of points on which the function takes a constant value. And actually, this is the minimum. This star denotes the minimum. So the function is like a bowl. It looks like an elliptical, a bowl with elliptical contours like this. And I'm starting my algorithm up there at the top, hoping to get down to the minimum with gradient descent. And you can see that my step sizes are too big, so that at some point I actually start diverging. I start marching up the function. It's just like this, but in 2 dimensions. That's what's happening. So if you fix t to be too small, then we won't have the problem of divergence. We still converge as long as the step size is small enough, but it's just slow. That's what the problem is. So here I've taken 100 steps with a very small step size, and you can see I'm actually still quite a bit away from the minimum. And as I get closer to the minimum, what's going to be special about the minimum in terms of its gradient value? 0. So the steps are actually going to shrink, right, effectively in size. Even if I have, even if t is 0.1, the effective step is actually 0.1 times the gradient, right? So what I'm saying is that if I'm slow to converge at this point, I'm going to be very slow to converge from this point on because the gradient's just getting smaller. So of course, if we could choose the step size just right, then we get very good conversions. I've done so in this example just by mostly trial and error, but the convergence analysis is going to give us a precise idea of what just right means. Actually, it wasn't even trial and error here. Because this function is a quadratic, I could work out from the theory very easily what the right step size should be. So I chose it according to the theory. Okay, so fixed step sizes, if they're about the right size, then we get very good convergence. And we'll give a precise definition of that in just a bit. An alternative to fixing the step size that's more popular and, well, okay, I guess it depends on the application. Depending on the application, people either take fixed step sizes or they choose them adaptively. But I think for the most part, there's not really any hurt in using backtracking for the types of problems we'll talk about today, at least. This is a way to choose the step size differently at every iteration based on what you think the progress is looking like. So the algorithm is as follows. Suppose I'm at iteration k. I'm trying to figure out what tk should be. Then I start with this value t, which I just initialize to be something like 1 or 10. I just pick some initialization for it. And I fix two parameters before I even started running gradient descent, call them beta and alpha. So this is a number between 0 and 1, and alpha is a number between 0 and a half. Okay, I think actually to simplify things, you can just take alpha to be a half, and you can just choose beta. Okay, just choose a shrinkage factor beta that you'd fix ahead of time. At every iteration, you basically are going to check this condition. And if this condition fails, then we're going to actually think that the step size that we're looking at, t, is a decent step size, and we're going to continue on, take a gradient step with that step size. If this condition holds, then we're going to actually shrink the step size by an amount beta and recheck it. So what this condition is looking at is the function value at the proposed gradient step, right? I'm at x. I'm thinking about going to x minus t times the gradient of f of x. Is it, let's say, larger than something like what I would see if I looked at a linear approximation to my function at x, and I degraded the slope by alpha? That's what this means. So I'll draw a picture on the next slide so it'll make more sense. If you're not making that much progress compared to a linear approximation after I kind of degrade the slope a bit, then I'm going to think that I should take a smaller step and recheck it. The moment that this is less than or equal to, then we take the step size t that first met this, and we actually take this gradient update. Okay, and then we run this to look to find a step size at x plus that performs well. Is there a question? Yeah. So I'm not sure that the function you're describing could be convex, right? So this type of function is not going to be convex. So it probably could get stuck, although we're not considering a case like that. That's a good question. Yeah.
So by this, we would never increase t, right? Like we'd always decrease it from what it's.
Yeah, that's right. So for this rule, we would never increase t. We could start with t net being very large, right? T net is like some fixed value that we always try when we start backtracking.
So if that condition, say that difference is huge, like we can see that our t is much smaller than it needs to be. Is there still any value to increasing it, or do we start with a large initial t?
Yeah, I mean, so you could increase. So let me draw the picture on the next slide, and then you'll kind of get, I think, the idea behind beta and what we could do to kind of address your problem. So here's the interpretation to backtracking. So I'm at this point, x. Okay, and this is my function. And I'm thinking about taking a step in the direction delta x. For us, delta x is just the negative gradient. Okay, but I took this picture from Boyd and Vandenberg, and they were looking at kind of a direction that's denoted delta x. And what backtracking does is it looks at the tangent line to your function at the point x. That's given by this guy right here. Okay, for us, remember that delta x was the negative gradient, so this part is the norm of the gradient squared, right? Minus t times the norm of the gradient squared for us. And we could never hope with a step size, with any step size, to achieve something that's lower than this line. right? Because the definition of a convex function is that its tangent line underestimates the function everywhere. So we can never take a step and somehow end up below this line. So what we have to do is we have to somehow degrade the slope of this by some fraction, alpha, before we make a comparison to how far we think how much progress we would make in comparison to a linear approximation. And that's what I'm showing you here. Okay, this is the same tangent line, but where its slope has been effectively multiplied by alpha. And alpha you can take to be half if you want to kind of simplify things. So what we're doing is we're comparing the step that we might take, like let's suppose we're going to take this step to what we hope to see from a linear approximation. And it's too big, so what we do is then we actually move back, we multiply t by a factor of beta, and beta is less than 1. So suppose we multiply by 0.9. That might put us here, and again we compare it to the linear approximation. It's still too big. Multiply by 0.9 again, and maybe it gets us to be somewhere here. Okay, and then finally we've progressed an amount that's smaller than or equal to something like what we think we should be doing with respect to this linear approximation, and then we're going to take that step size. So maybe to address the question that was just asked, let's first kind of start thinking about another question, which is, what is the problem with taking beta to be really small, like let's say 0.1 or 0.2? What could possibly go wrong if I took beta to be too small?
You make the gradient descent very slow.
Okay, I think that's true, but let's break it down a bit more. So what would be wrong with the step we took if beta was like 0.1 or 0.01? Compared to, so this is the step. Let's suppose that the moment at which our function actually intersects this linear approximation, that's kind of like the step we want to be ending up at when we backtrack, right? We want to kind of just get the biggest step size possible until this condition is met. Because big step sizes are good, and this condition is telling us that we're going to be descending, at least with respect to a linear function in some way, right? So we want to end up with the largest value of t for which this is met. What happens if I take beta to be really big and I run this algorithm? Sorry, really small. If I take beta to be really small, like 0.01. What's the matter with the strategy? The step size can be, I could way overshoot it, right? I could be here, and I could say, oh, it's not. I don't have the proper direction yet, right? I still have my function lying above the linear approximation, and I multiply by 0.1, I end up out here. So it's definitely met, but I just have a way too small step size as a result. So we could overshoot kind of where we want to end up with backtracking, right? We could be basically just considering too small of a step size by the time that we exit. If beta is too big, then we're just going to have to run many backtracking iterations to get to this point, right? If beta is 0.999, then we're doing many backtracking iterations just to get to this point. But by the time that we actually reach the exit condition, we'll be kind of close-ish to the step that we want to take. Okay, so that's the trade-off in choosing beta. So to answer a question that was asked a bit earlier, one thing we could do, although I don't think it's really done very commonly in practice, is if we take a small value of beta, which means that we take big shrinkage and we end up, say, here, and it's just too small of a step, then we could actually increase the step size if we wanted to. Maybe even some kind of binary search, right, until I think that I meet this exit criterion with the largest possible value of t. I'm not really aware of that being done so much, but I guess that doesn't seem to be anything wrong with that. Yeah?
Why do you choose alpha to be less than or equal to a half?
That's a good question. The best answer to that question comes from the convergence analysis. If alpha is chosen to be larger than half, then it's not clear that essentially backtracking will give us a convergent algorithm. So I'm not sure how else to answer other than that if we look at the convergence analysis for backtracking, there's a particular step that we can see that this condition is essentially going to imply to us that gradient descent is actually descending. But if alpha is taken to be too large, that won't necessarily be the case.
So does actually choosing alpha depend on kind of the shape of the function you're trying to?
Yeah, certainly the right values of beta and alpha do depend on the shape of the function. Both of them do. People don't really pay a lot of attention to optimizing these parameters. In fact, the Boyd and Vandenberg book suggests that you take beta to be 0.8. That's just their generic suggestion. Certainly it's going to be like depend, whether that's a good idea depends on your particular function, but we don't spend a lot of time usually optimizing these parameters. That's why I said you can just fix alpha to be a half for simplicity and then think about taking beta to be something, you know, close to 1 but not too large. All good questions. Yeah, another question.
But it is very expensive to evaluate function f. You want to do the
Yeah, you're absolutely right. So in some cases, it's expensive to evaluate f. It could also be expensive. Yeah, well, okay. Here, this could involve evaluating f multiple times. We're not actually evaluating the gradient more than once, right? So that's the good thing about backtracking. If the function itself is expensive to evaluate, then you probably want to take beta to be actually kind of small, because then there'll be fewer inner iterations of backtracking, right? You'll meet that extra criterion kind of quickly. Good questions. Okay. So here, this was the example with the same I showed you before, but instead of fixing the step size, I just chose the step size via backtracking at iteration. You can see it actually takes quite different lengths of step sizes depending on the iteration, right? Because in some cases it thinks that it should be taking a larger step size than other cases. And it converged to about the same degree of accuracy as what I saw before with this picture in only 12 steps. But if we want to be counting kind of total number of iterations, right? So backtracking actually has us evaluate the function a bunch of times in the inner loop. Then this actually ended up being 40 steps total if I count all the iterations, including the inner ones from backtracking. So it ended up being about the same as if I had chosen the step size kind of just right as a fixed value. Okay, and here just for the example, I had alpha and beta both set to be a half. So another option for choosing the step size, there actually are many other ways to choose step sizes. I'm just showing you the most common one, I think, which is backtracking. One thing that people sometimes think about, which I thought I'd mention, but I don't think is generically a good strategy, is to do an exact line search. So, given that we're looking at directions given by the negative gradient, you might say to yourself, why don't I just look at all directions given by the negative gradient? I'll just try to optimize my criterion value in the direction given by the negative gradient over all possible step sizes s. And I'll take t at any given step to be the one that exactly minimizes that. That's called exact line search. So rather than backtracking, which is a very rough approximation to this based on linear approximations to our function. Let's ask the question first, just as a quiz, given that we just did a bunch of stuff on convexity. Is this problem even well defined? Meaning, is this even a convex problem? If f is convex?
Yes.
Okay, it is. So why is it a convex problem?
It's a affine function convex.
It's an affine function than a convex function. Yeah, I guess we could think about it. It's a composition of a convex function and an affine function. Yeah, sure. I think that's certainly a way to think about it. It's a good answer. Another way to think about it is that this is taking a convex function and restricting it to lie on a line segment. Okay, and we'll also learn that if f is convex, if and only if it's convex on every line segment. So if f is convex, then I can look at this direction, right? The direction given by the negative gradient. I suppose the negative gradient is pointing me in this direction. I can look at this line segment, and if f is convex over all of Rn, it's going to have to be convex in this line segment. So it's certainly a convex optimization problem. So the reason that I said this is not a good idea is that usually it's not possible to do this minimization exactly. Usually we just can't find such a value of s. And in fact, the only times that we really can do this is if f was a quadratic. And it's only really helpful when f is a quadratic with kind of weird curvature. Besides that, I don't think I've seen people using exact line search pretty much at all. It's usually much simpler to use backtracking, and it's you don't gain much by trying to optimize this. By trying to optimize the step size exactly, or even approximately optimize the step size. I could think of this as a separate optimization problem, right? It's a one-dimensional optimization problem, but then I could throw my favorite one-dimensional optimizer at this problem to try to find the right step size at each step. Usually it's not worth it. Usually, backtracking is just as good, or it's close enough. So let's see. I think we can go ahead and do the convergence analysis and then take a break, because we actually have a bit of time before we usually break. So let me pause for questions first before I do the convergence analysis. Any questions about gradient descent so far? Yeah.
When talking about the convexity of that function, isn't the argument for variable x, both arguments made with variable x, whereas I think we're considering the argument over variable s. Shouldn't we be making the argument of convexity the function of s?
So both arguments were considering s as the variable and x being fixed. Right? So x is just some fixed point, and it defines x and its gradient define for us a line segment. Right? This is maybe the line segment defined by x minus the gradient of f of x as s varies. But s is the optimization variable, or it is the variable that we're talking about when we talk about convexity of this function. Okay? That was good to be clear. Other questions? Okay, so let's do the convergence analysis. So this is going to be our first one, and maybe probably our only one for this unit. And we're going to prove the following fact. So if f is convex and it's differentiable and it has a domain all of Rn, that domain is constrained is just kind of for simplicity at this point. I mean, the fact that the domain is all of Rn is just for simplicity at this point. And we're going to additionally assume the following, which is something you are probably, or you should be, familiar with at this point given your first homework. The gradient of f is Lipschitz continuous with a constant L, which means that if I evaluate the gradient at any 2 points x and y, then the distance between the L2 distance between those two gradients is less than or equal to L times the L2 distance between x and y. That's what it means to be, for a function's gradient to be Lipschitz continuous. So we're going to assume this is true. And given these facts, which are, I think, pretty innocuous, right? Convex differentiable function, full domain, Lipschitz continuous gradient, we're going to prove that gradient descent with a step size that's anything less than or equal to 1 over L satisfies the following inequality. At every step k in the algorithm, the difference between the criterion at xk, which is, remember, it's the kth point we visited in gradient descent, and the optimal value, f star, is less than or equal to the L2 distance between where we started and a solution, x star. So this theorem is true for any solution, x star. If there's more than one, then it's true for any solution, divided by 2 times t times k. So what that means is that we can expect the error, right, that we incur, or the suboptimality that we incur, to go down as like something times 1 over k. Okay, it should be going down like 1 over k. That's why we say that gradient descent has a convergence rate of 1 over k, because after k iterations, the suboptimality that we incur, if we look at the kth iterate in gradient descent, is like something times 1 over k. We can also flip this around. We can flip it around. And we can say, if we want to have a suboptimality of epsilon, if I want to go enough steps to get a suboptimality of epsilon, how many iterations do I need? How big does k need to be in order for this to be true? That was not what I wanted to do, right? And we just flip that around, right? I say, suppose that I know that this quantity upper bounds suboptimality of my function. I want to choose k to be big enough so that basically the suboptimality is no more than epsilon, right? Because this upper bounds my suboptimality. So how big does k need to be? Just rearrange that to see that I need to have k to be 2t over the distance between no, that's wrong. It's just exactly the same expression, but replacing k by t. Okay? It's just flipped around. And so that's why we can also say we have two notations we're going to be using for convergence rates, k and epsilon, and they kind of mean different things. But in this case, it's the same rate in either case. So if we want a suboptimality of epsilon, we need order 1 over epsilon iterations. Okay, I tend to prefer this one. I think this one is easier to remember, or it's easier to explain what that means, I think. Okay, so we're going to prove that. Right, so the largest step size we can take, just to say it out loud, is 1 over the Lipschitz constant. And we benefit from taking larger step sizes because, look, if the larger t is, the better this bound is, right? Because t is in the denominator. So in this example, I computed the Lipschitz constant of the function, of the gradient of the function, and I took t to be 1 over the Lipschitz constant. That's how I got that step size. And that was easy to compute because that was my function. It's just a quadratic function. So its gradient, right, it's just linear. Okay, let's go through the proof. And proof of the convergence rate for proximal gradient, which you'll do in your homework, for homework 2, it's going to be somewhat similar to this. So, you know, it'll be helpful to understand this proof because it'll also help you with your homework. The first, I have kind of a proof outline on the slides, but I'll do it in more detail on the piece of paper. So the first step that we use is that because grad f is Lipschitz with constant L, we know from homework 1, right? Remember you proved this on homework 1, that we can essentially upper bound f by a quadratic at any point. And this is the quadratic. Okay, this is true for all x and y. So this is an important factor in our proof. And now let's suppose that we are at x in the gradient descent iterations. And we're going to go to x plus, which is x minus t times the gradient of f of x. And I guess if it wasn't clear, maybe I didn't say it in words, this is a theorem for fixed step size. Okay, we're taking the same step size for each step. A theorem for backtracking will appear just in a few slides. So we can use the above, right? We can use the above inequality with y equals x plus, because that's going to tell us how big the criterion is at x plus compared to the criterion at x. It's kind of exactly what we want to know, right? We want to know how much did we decrease the criterion by going from x to x plus. So this is a very helpful inequality for that purpose, because this tells us, you know, comparisons between f of y and f of x for any points x and y based on the gradient and their distances. So when we do that, we see that f of x plus, right, is less than or equal to f of x plus the gradient of f of x transpose. Now what's y minus x when y is this value right here, x plus? It's just minus t times the gradient, right? And it's the same thing here. We just get minus t times the gradient. All I've done is I plugged in for the definition of x plus, the next step, and I'm just going to simplify this stuff. So this is f of x minus t times the norm of the gradient squared. Right? That's what I get from this term. And from this term, I get plus L t squared over 2 times the norm of the gradient squared. And these terms both have a norm of the gradient squared, so let's combine them. I can write this as minus, should be, let's say, 1 minus L times t over 2 times t times the norm of the gradient squared. Okay, let's hope that's right, because I get minus t from this, and from this I get plus, because I have 2 negatives, lt squared over 2. Okay, so let's just pause here and think what we got. So the strategy was pretty simple, right? We just used this inequality from the fact that grad f was Lipschitz to compare what happened at our next step to what happens at our current step in terms of the criterion value. And look, we actually have something quite nice, because if t is less than or equal to 1 over L, notice that we get f of x plus to be strictly less than f of x. Actually, I should say less than or equal to, because if t is strictly less than 1 over L, then we get strict descent. If it's less than or equal to 1 over L, we get f of x plus is less than or equal to 1 f of x, just from this inequality, right? If I take t to be less than or equal to 1 over L, then this thing, yeah, then in fact, we get even better than this. Let's write down what we get. We get f of x plus is less than or equal to f of x minus t over 2 times the norm of the gradient squared. So I guess I was kind of stopping kind of short of what we can say. If t is less than or equal to 1 over L, then this thing is bigger than or equal to half. So we can make this inequality. Okay, so an important aside. We get descent, which means that f of x plus is strictly less than f of x. Let's put that in brackets. So now we've shown that if t is taken to be smaller than or equal to 1 of the Lipschitz constant, we actually do get descent and gradient descent. Okay, and actually it's even more than that. Is we have this inequality. Where we are at x plus is less than or equal to where we were at x. So from one step to the next, minus something that's positive. Okay, so we're not quite where we want to be, because we actually want to compare f of x plus to f star. Right? We want to ask how far are we away from the optimal criterion value. This is just how far we are away from the last criterion value. Right, so we want on the right-hand side is something like f star plus or minus a bunch of stuff. So we can let's use convexity first. Using convexity of f. And we can use convexity right, we can use convexity around the point x. So by convexity of f, f must lie above its tangent line everywhere. So in particular, that must be true at the point x. So this is what we know from convexity of f, right? And also the fact that f is smooth. And another way of saying that, just by rearranging, is that f of x is less than or equal to f of x star plus the gradient transpose x minus x star. I've just rearranged that inequality. Okay, so this is kind of exactly what we want, because, like I said, we wanted to have f star on the right-hand side. We wanted to compare where we are at our iteration compared to the optimal criterion value. And so now we're going to upper bound f of x by this quantity to continue on with the bound. So coming from this step, okay, we're gonna say that at the next iteration, we're less than or equal to f of x star plus the gradient at f of x transpose x minus x star minus t over 2 times the gradient of f of x squared. Okay, so we're getting quite close. Rearranged, maybe we just want to move move the difference between where we are at x plus and the optimal criterion value to one side, because that's the thing we want to bound, right? Okay, so far I think the proof is really, it's maybe been, just seeing it written down for the first time, looking like it's kind of following a bunch of mathematical steps that you don't have much intuition for. I think that actually everything we've done so far is pretty natural, right? Because we're just trying to get a bound on f of x plus minus f of x star, and we've used, the only two tools we used are Litschiff's of the continuity of the gradient and convexity of f. Those are like the two fundamental inequalities that we know, and we use them both just in the appropriate way to get a bound on this distance down here. This next step is, I think, that really the only part in the proof that's tricky. I think if you went through this proof a few times on your own, you would not find it tricky, except for possibly this next step. And you have to just realize that this right-hand side can actually be written as a difference of two terms. And sometimes people actually prove the gradient descent rate using this step as the first step, although I don't think that's very helpful. This is the only kind of tricky step. So we're going to write this as the difference between the norm of x minus x star squared and the norm of x plus minus x star squared times 1 over 2t. It just so happens that this quantity right here, the gradient of f of x transpose x minus x star minus t over 2 times the gradient of f of x squared, is actually equal to some constant, and that constant is 1 over 2t, times the difference in square distances between where we were in optima and where we are now in optima. And to check that, you can just expand. Okay, so to check that, just expand. So, we can even do it here. X minus x star squared minus, so what's x plus? X plus is x minus t times the gradient of f of x minus x star squared. And we're just going to expand the the second term. Just expanding the square. And here I'll group actually this on its own and x minus x star together. So from the x minus x star term, I just get that squared, right, which cancels. And from the this on its own, I just get t squared times the norm of the gradient of f of x squared. That's from squaring this. And then the cross term, right, is going to be 2 times t times the gradient of f of x transpose x minus x star. Okay, so what's left over once you multiply through by 1 over 2t, you just get minus 1 over 2t, minus t over 2 times the norm of the gradient squared plus grad f transpose x minus x star. Right, that's what I claimed, that this could be written as a difference between two terms. Okay. Okay, so I think that's really the only kind of tricky step in the proof. Okay, so we're almost done. The proof's, I think, pretty much complete. So let's just back up and state what we have in terms of k. So what we've shown is that at any iteration, say iteration k, f of xk minus f of x star, right here I'm thinking now of x plus as xk, and x as xk minus 1. This is less than or equal to 1 over 2t times xk minus 1 minus x star squared minus xk minus x star squared. Okay, and this is very nice because if you think about what would happen if I summed this over all k, a lot of these terms would cancel. It would be a telescoping sum. So now let's sum this. Maybe I should have used I. I'm sorry if I'm making this messy. It may have been more clear if I used I as the iteration up here in terms of an iteration I. Because I'm going to want to sum with the endpoint of the sum being k, just not to confuse you too much. Okay, so sum this over all iterations I from 1 to k. This is all, a lot of these terms are going to cancel, right? Because I'm going to see, for example, minus xi minus x star in this term, but in the next term, right, where I have I plus 1 here, I'm going to see a positive xi minus x star. So all these terms are going to cancel except for two terms, right? And the only two terms that are going to be there are basically the very first term. So when I was 1, so I get x0 minus x star squared, and the very last term when I was k. And we can further upper bound this just by getting rid of this. Okay, this term xk because it's negative. Okay, so now this should be looking quite familiar given the rate. This is pretty much the rate that we proved. It was this divided by k, right? So where does that come from? Well, here we have the sum of the suboptimalities across all iterations going from 1 through k. But because we've proved that we have a descent method, because we're actually descending on the criterion right at every iteration, I can certainly say that that this is true. Where I am at step k is less than or equal to the average of the suboptimalities along the way. Right, because this guy is certainly less than each of the f of xi along the way. And just following from what we've proved about the sum of the suboptimalities, that's exactly our rate, right? We just get x0 minus x star squared over 2t times 1 over k. Okay, questions about that? It's perfectly clear. Makes sense to everybody. Okay, great. Just kidding. Let's take a break. We're a bit past the break period. Maybe you'll have some questions when I get back. There needs to be. Were there any questions about the proof? Yeah.
Could you explain why the f(x) one is smaller than the
Sure. So this property here.
Yeah.
So that came from the fact that we chose the step size to be small enough. So if you remember, at the start of our analysis, we said that if the step size was less than or equal to 1 over L, then at every step where we are compared to where we will be, we have this inequality. F of x plus is less than or equal to f of x minus t over 2 times the norm of the gradient squared. Now this can only be non-negative, right? So that gives us that inequality. Oh, I just wrote it backwards. That's probably why you're confused. I'm sorry. Of course, that's supposed to be the way around. Thank you for catching that. Now this just looks like two inequalities competing with each other, but
Okay, now can prove the
okay. Now it's just a typo, or righto, whatever you want to call it. Okay, thanks. Other questions? Yeah.
Question from the condition that t must be less than 1 by L, it seems that it can be the case that t can be less than 2 by L, because if LT is less than 2, then that term.
Yeah.
So is there something else?
It's a good question. So if t is you're right, if t is made bigger, we still get descent. But we probably won't get the same rate. Where did I write it down? Yeah, this form is actually important for getting the rate at the end. So we can take a larger t and still get that we're descending, but this is important for kind of proving the convergence rate that we got. And the question earlier was about alpha, I think about backtracking, right? This is where we need to have alpha at most a half. Because actually, when we do the proof for backtracking, which isn't in the slides, but it's quite similar, we establish a very similar condition. In fact, just look at this condition. Okay, if alpha was a half, this is the backtracking exit condition, right? We will not exit backtracking until this condition is met. This is precisely the backtracking condition. So for the proof of backtracking, we can actually just start here. Okay, and then the proof proceeds basically the same way. Okay, good questions. Other questions? So, okay, I had it up on the slides here. So the convergence analysis for backtracking is very similar. We basically start by asserting that line I was just pointing to. And it's essentially the same result. We get a convergence rate of 1 over k. It's just that the effective step size in the denominator is a bit different. That's it. And here I'm assuming that you start every backtracking round by taking a t init to be 1. If your initial value for the backtracking search was not 1, then you just would put it in there. So backtracking provides us with the same rate. But the nice thing is that we don't have to actually be tuning the step size, right, to be smaller than or equal to 1 over the Lipschitz constant, which in many cases would be an unknown or just hard to compute. It might be kind of hard to compute the Lipschitz constant of the gradient. So backtracking is nice because it doesn't require us to have such a restriction on the step size to begin with.
How to do a right at t-min?
This is a definition. I'm just defining t-min to be the minimum of 1 and beta over L, where beta was the parameter we used for backtracking and L was the Lipschitz constant.
You must have thought about how to do actually a right at this expression.
Oh, I mean, I'm not showing you the proof. The proof is similar to this.
Which part of the proof that we
Well, so the thing is that in backtracking, it's a different step size at every iteration, right? So this was kind of like an analysis of what happens at a given iteration between x and x plus. Backtracking would choose some value of t there, but that would be different across each iteration. So for backtracking, when you go to this notation, where you think about what happens at an arbitrary iteration in terms of this notation I, the step size that you see here is actually ti. It's a different iteration for each, a different step size for each iteration. And to kind of combine them, this is the way that we can bound it. That just happens to be the convenient way to get a final bound on the expression. Okay, I think in previous year's notes I have the proof for backtracking in the slides. So you can take a look at that, or people are welcome to stop by my office hours if they want to see more details on that. Okay, so I wanted to point this out, which is important. Wow, time really flew by. Which is that if we have a strongly convex function, then convergence analysis is actually quite a bit more favorable. So if f is strongly convex, which remember means that f is lower bounded by a quadratic, that's something you also proved in homework 1, then we get quite a bit more in terms of the convergence analysis. We're also assuming that here grad f is Lipschitz. So when f is both upper bounded and lower bounded by a quadratic, which means that it's strongly convex and it has a Lipschitz gradient, then gradient descent achieves a much faster convergence rate than what we saw in the previous analysis. And in fact, after k iterations, it looks like something times c to the k, where c is a constant that's less than 1. So rearranged, we could say that if we wanted to get the suboptimality to be less than or equal to epsilon, if we wanted to take a number of steps k for which we had an epsilon suboptimal solution xk, then we only need log of 1 over epsilon iterations. So compare that to 1 over epsilon iterations, right? That's much fewer iterations, much fewer iterations. So something you may see in optimization literature, like in the Boyd and Vandenberg textbook or just papers and stuff you might read, is that this is called linear convergence, which is kind of strange because if somebody asked you what kind of function c to the k is as a function of k, you would never call it linear unless you were doing optimization research. And that's because we typically plot the suboptimality versus iteration number when we look at convergence of these algorithms on a semi-log scale. So the y-axis is usually on a log scale. That's just the kind of convention in optimization. So if we were to plot this suboptimality on a log scale, then a rate like this, log of 1 over epsilon, looks like a straight line. That's all. That's why it's called linear convergence. Okay, it looks like you get a straight line on such a plot. So that's much more favorable than the rate 1 over epsilon, right? Log of 1 over epsilon is much more favorable than 1 over epsilon, but we need strong convexity in order to get that. And strong convexity essentially implies that there's enough curvature on the minimum, right, that gradient descent is going to converge very quickly to the solution. Because when you have a strongly convex function, the solution is unique. So we can say the solution, right, not just a solution. In the analysis, this constant c depends on the condition number of the Hessian, which is the ratio of its largest eigenvalue to its smallest eigenvalue. And from homework 1 again, if you can see that if the gradient was Lipschitz, then the Hessian has largest eigenvalue at most L, and it has smallest eigenvalue at least M. So the condition number you can think of as L over M. Okay, the ratio of its Lipschitz constant to its strong convexity constant. And if this condition number is higher, then it means that the function has kind of it's more adverse. It has a curvature that's not very spherical, and the rate actually can be slower that we derive when it comes to this constant c to the k. This c can be like very, very close to 1, so that we don't actually get nearly as fast conversions. Okay, so it's just something to note that for gradient descent, both the rate and also the practical performance, it depends on the conditioning of the function. Right? If the condition number is large, then both the rate we prove and also the practical performance degrades. And it's something to keep in mind when we kind of think ahead, and when we talk about second order methods, that's not going to be the case. Second order methods are not going to depend on, they shouldn't depend on condition numbers in terms of the speed of their convergence. Okay, simple look at the conditions. I'm just going to do this very quickly because I hope that this is more or less review for most people. And if it's not, then just spend a little while looking at this slide because, again, this is just kind of basic multivariable calculus stuff we're talking about. So I just wanted to show you what the conditions would look like if we were thinking about least squares. Okay, we wouldn't really optimize least squares by gradient descent. I mean, unless the problem was enormous and we wanted to use stochastic gradient descent or something, but still that's not always what's done. But let's just think about what would happen if we wanted to optimize this function this function with gradient descent. So what does it mean to assume that the Lipschitz, that the gradient is Lipschitz? Okay, that means that, if you calculate it out, that we have an upper bound on the largest eigenvalue of the Hessian, but the Hessian is just x transpose x. So this is true as long as the Lipschitz constant is the largest eigenvalue of x transpose x. So here I've written it as the largest singular value of x squared. So that's always true. It's just that we may not always know the Lipschitz constant. It could be expensive to compute that, right? We wouldn't really want to compute that necessarily if we could avoid it. Strong convexity, on the other hand, right? We essentially can do the same calculation and see that we have strong convexity as long as the smallest singular value of x is not 0, if it's bounded away from 0. And in that case, the strong convexity constant is going to be the lowest eigenvalue of x transpose x, or the smallest singular value of x squared. And from that, we can see that as if we're in a high dimensional case, if we have predictor matrix x, which is n by p, and p is large, like larger than n, then it's not going to be strongly convex. We already kind of went through an argument like this earlier, right? And even if it is the case that we do have strong convexity, if x is not very well conditioned as a matrix, then the condition number of our problem is going to be very poor. It's the ratio of the singular values squared. That's just a look at the conditions for a somewhat familiar problem. Okay, I'm going to skip over this. I wanted to just say one more thing before we end, and then next time I'll just tell you what stochastic gradient descent is so that we don't forget that. So this is an important thing to think about, and we'll talk about optimality a few times throughout this unit. So what we proved is that gradient descent has an order 1 over epsilon convergence rate over the problem class of convex differentiable functions whose gradients are Lipschitz. And let's formally define a first order method now so we can make an interesting statement. So a first order method we're going to define as just an iterative method where we produce a sequence of iterates like x0, x1, x2, x3, etc., where at any step xk has to lie in the set x0 plus the span of the gradients we've already seen. Okay, so we visited, say, k minus 1 gradients so far. Take their linear span. Okay, so take all linear combinations of these vectors, add our initial point. As long as our algorithm places xk somewhere in this set, then we're going to call it a first order method. So something you should check, just to check that you understand, gradient descent is you should check that gradient descent is indeed a first order method. You can actually prove that by induction. Okay, just think about why gradient descent makes updates that lie in this set. So there's a very nice and important theorem by Nesterov. And this theorem is, it's actually not that old. It's from the 80s. I think it's from 1982, in which Nesterov shows that if you give me any function that has a convex differentiable, let's kind of rephrase that. So if you give me any initial starting point and you ask me what happens after iteration k, for an arbitrary iteration number k, then Nesterov proves that there is a Lipschitz, a function who's convex and differentiable and has a Lipschitz gradient, such that all first order methods cannot be converging on the criterion faster than this rate. So this is a lower bound on how well we can expect to do. And this rate is actually something quite similar to what we saw. It's the distance between where we started off in the solution times the Lipschitz constant divided by, this is the key difference, k squared rather than k. So we've actually established an upper bound that gradient descent, for any convex differential function with a Lipschitz gradient, it has essentially this same right-hand side divided by k. And what Nesterov has proved is that no method can be better than 1 over k squared. So now we see there's actually a gap. It appears that we've proved that gradient descent attains the rate 1 over k, but this is the optimal rate, 1 over k squared. So you could ask yourself, what method attains this rate? Right? There actually is a first order method which is doing something very similar to gradient descent that could be doing better. So what method attains that rate? And we're going to actually see that method is a very simple kind of modification of gradient descent. And we'll get to it kind of towards the end of this unit. So, okay. See you guys next week.